Next, I'll go into more detail about the high-speed digital to analog converter portfolio and how these products service the various microwave system architectures. This diagram shows a quick view of the DAC requirements for each of the system types. Similar to the ADC sampling requirements, the DAC sample rate must be at least twice the channel spacing requirement for a given system. The QAM density achievable by the DAC is correlated to the noise spectral density performance of the part. The lower the noise floor of the DAC, the higher the possible signal-to-noise ratio, and therefore the higher the modulation scheme that can be supported. Just like ADCs, the E-band systems require higher sample rate DACs, but do not need the higher noise performance capabilities that the traditional band systems require. Many of the DAC product options support both the traditional legacy band requirements as well as the E-band wide bandwidth requirements. The AD9122 and AD9142A are two versatile dual DAC products that can be used in either system design, enabling some design reuse across systems. The AD9139 single DAC is the highest bandwidth capable LVDS IF class DAC, requiring only a single LVDS port. The AD9993 MXFE product integrates a dual DAC and quad ADC functionality into one chip, both with 14-bit resolution, making this product a great solution for the traditional full ODU application, including ADCs to use for DPD algorithms. As we move into the JESD204B SerDes interface products, the AD9152 dual DAC supports the high performance criteria needed for the legacy bands, whereas the AD9136 and AD9135 dual SerDes DACs provides the ultra-wide bandwidth capabilities required in the E-band system architectures. This table shows a comparative look at the LVDS IF DAC options for the point-to-point systems. These products are able to support the traditional band microwave systems as well as up to the 500 MHz channel separation E-band system. All but the AD9129 have an on-chip PLL, which eases the clocking requirement for these products. The resolution of these products is sufficient to meet the performance requirements of the higher modulation schemes in traditional band. The AD9993 MXFE is a well-integrated product providing support for both a dual transmit and dual receive path with an additional dual ADC that can be used for DPD algorithm loops. It's a low-power solution which also provides PCB board space savings when compared to similar designs using discrete components for transmit and receive paths individually, allowing for a reduction in the overall total cost of the system. Some of our earlier LVDS products, like the AD9125, can be used for the traditional band systems by supporting a max data rate of 250 megasamples per second. The next generation AD9142A dual DAC provides more than double the sample rate of its predecessor, with a max data rate of 575 megasamples per second, supporting up to 250 megahertz channel spacing for the E-band systems. These dual DAC configurations are paired with an onboard low-pass filter, followed by an IQ quadrature modulator providing an RF output. For even further wider bandwidth applications using LVDS, two AD9139 single DACs can be synchronized and used as an IQ complex pair in a similar configuration as the dual DAC shown here. The AD9133 can support a maximum data rate of up to 1.15 gigasamples per second per DAC, providing up to 500 megahertz of data bandwidth for the higher channel space E-band systems. The AD9135 and AD9142A are some of the highest performing IF class DACs available, with superior spurious and noise performance that meet the strict requirements of the multi-carrier GSM spec, and are versatile products for a variety of applications outside of the microwave point-to-point systems as well. Recently, ADI's converter portfolio has begun to focus on developments that include the new JESD204B serial interface protocol. The SerDes interface provides the capability to pass data at much higher bus rates than is feasible with the LVDS interface. By increasing the achievable data rate throughput rate, higher bandwidth applications can be supported much easier with this new interface configuration. ADI has a variety of SerDes IF class DACs that all support data rates of at least 1 gigasample per second, with the AD9136 and AD9135 supporting up to 2 gigasamples per second. These SerDes IF DACs follow a similar transmit signal chain as the LVDS IF DACs, with wider low-pass filters to support the wider bandwidth capabilities, and new IQ quadrature modulators that easily interface with these various products to make system design simpler. This comparative chart of the JESD204B SerDes IF DAC products for point-to-point systems shows how the shift from LVDS to SerDes interface designs enables even wider complex data bandwidths than are achievable with LVDS. All these products provide greater than 2 GHz DAC sampling rate, higher than any of the IF-class LVDS DACs in the portfolio. The quad 809154 and 809144, along with the dual 809152, can support the E-band systems up to 500 MHz channel separation. They have companion IQ quadrature modulator chips also available from ADI to enable a full signal chain design. These DAC products have on-chip digital modulation for baseband data modulation internally, as well as an integrated PLL to eliminate the concern regarding clocking signal integrity at the higher sample frequencies. Depending on the type of architecture design chosen, different products are better fits for the system needs. For high complex IF applications, the 809154 and 809152 provides high spurious-free and noise performance for these systems and are the best choice for these types of architectures. For low complex IF or zero IF systems, the 809144 is a good fit for these needs and provides a lower power solution in comparison to the other product offerings. The main target for the upcoming E-band architectures is pushing the channel spacing requirements even further than before, out to 1 GHz or even higher separation. The 809136 and 809135 can provide these ultra-wide signal bandwidth capabilities, up to 1 GHz channel spacing, and are a great solution for these fast-evolving E-band systems. I will focus in a bit more detail on the capabilities of these two products and how they are well-suited for the E-band architecture in the next few slides. First, for some context on a general block diagram of these IF-class DACs, this diagram shows the 809144 product features as an example. The 809154 quad DAC and 809152 dual DAC have relatively identical product features and lineups to the 44, so this diagram can serve as an overview for all these products. The 809144 and the 809154 have 8 SerDes lanes. The 9152 only has 4 lanes, which provide the high-speed serial data from the FPGA to the DAC for processing. These products have programmable interpolation filters providing 1x, 2x, 4x, and 8x interpolation options for the user to upsample the data and push the DAC sampling rate and images higher to be out of band of the intended signals. There is an on-chip tunable NCO that performs complex modulation on the input signal when enabled, and also a programmable phaseward offset control. There is an inverse sync filter to improve in-band flatness and counteract the sync roll-off of the DAC, followed by a digital gain block to amplify the signal back to a desired level after the filter has leveled off the signal band. Additionally, there is a digital phase and DC offset control that can be used to optimize the image rejection and LO leakage at the output of the quadrature modulator that follows in its path. These parts additionally have a power detection protection block that monitors the input signal received from the FPGA and calculates the average power. If the power level calculated goes above a programmed threshold value in the part, which is user-defined, the part can trigger the data path to be ramped down to mid-scale and mute the DAC outputs to protect the power amplifier that is often at the end of the transmit signal chain. This block also has output pins that can be routed to a PA as a trigger signal to shut down the PA so it's protected from any peak power spike that may occur in the data path due to degradation of the serial link or other factors causing errors to be transmitted. All of these products contain an on-chip PLL to eliminate the need to route a high-frequency DAC clock signal on the system board. They also have multi-chip synchronization capabilities, including support of the SerDes subclass 1 classification for more accurate sync using a sysref signal, which is often critical to the design of any complex communication system. The 809136 and 809135 are dual converters and have many of the same features as the 9144, 809154, and 809152 products. They have the same selectable interpolation modes along with 8 SerDes lanes capable of supporting up to 10.6 gigabit per second lane rates. These products include a SerDes mode that allows 4 SerDes lanes to feed each converter for a maximum data rate capability of 2.1 gigasamples per second, enabling support of the 1 GHz channel spacing bandwidth requirements for the newer E-band system target. These products have digital functionalities such as inverse sync, digital gain, and DC offset controls, like the other SerDes IF DAC. They have the same integrated DAC PLL for simpler clocking and multi-chip synchronization capabilities. Regarding performance, the 809136 and 809135 have solid SFDR and IMD performance at the 2 GHz DAC sampling rate. The ACLR performance for a 1-carrier WCDMA signal at an output frequency of 150 MHz is 80 dBc, and noise performance is down at minus 163 dBm per hertz for a full-scale signal. These parts have relatively low power consumption, around 700 milliwatts per channel, when operating at a 1.6 gigasample per second DAC rate with full digital feature sets enabled. The 809136 is a 16-bit resolution part, and the 809135 is an 11-bit resolution part. Overall, these products provide the necessary performance and bandwidth requirements for the high channel separation E-band system. The spectrum analyzer capture was taken at the 809136 DAC output. It's a 900 MHz ultra-wide bandwidth signal with the DAC running at 2 GHz and 1x interpolation selected. The SerDes mode configuration uses 8 lanes to feed 2 converters for the maximum SerDes lane rate of around 10 gigabit per second. The inverse sync filter is enabled to help improve the in-band flatness response of the wideband signal. The plot here shows the 809136 noise spectral density, or NSD, performance of the part. The DAC is sampling at around 2 GHz for these conditions and shows the noise performance as the input signal level is digitally scaled back. As seen by the plot, the noise performance is as low as minus 165 dBm per hertz across the entire output frequency range when operating with the digitally back-off signal, which is common for most communication system designs. This picture shows the ACLR performance of the 809136 with a 4-carrier WCDMA signal output at 122 MHz. The internal PLL is used to generate the 2 GHz DAC clock. However, it shows minimal impact to the adjacent channel performance of the part, showing around minus 76 dBc performance for a total carrier power of minus 9.7 dBm. This slide shows the current evaluation boards for the SerDes IF class DAC. There are 2 evaluation platforms available. One is our DPG3, or data pattern generator, that supports up to 8 gigabit per second lane rates for the SerDes interface. The second is the ADS7V2, which supports up to 12.5 gigabit per second lane rates. The 2 different DPG3 compatible boards available for each DAC are DAC-only evaluation boards and a DAC plus modulator evaluation board variant. The DAC-only eval board provides access to the DAC outputs directly for evaluation. The DAC plus modulator boards have the additional option to evaluate the performance of the full DAC plus modulator signal chain at the RF output directly. Both of these board variants have additional ADI components that can be seamlessly incorporated for a more complete signal chain solution. The 80 clock 925 clock buffer and 809516 clock distribution chip are on both of these boards, as well as the ADRF 6720 quadrature modulator, included on the DAC plus modulator board variant. The ADS7 eval boards are FMC compatible. They also interface easily with other FPGA vendor evaluation kits through the FMC connector on board as well. These boards provide outputs to evaluate the DAC performance directly and also include the 80 clock 925 and 809516 clock solutions, in addition to an optimized power supply solution. All of these boards are currently available for ordering through our website.